That's the way to do it. We'll talk about this kind of curve later on more. This is the example we have. The K1 is the system, the K2 is the TMV of the spring. Okay, like that. Okay, the next, let's talk about this. I think maybe I will try this, maybe we'll see what happens. Maybe we skip this. Maybe we can skip this and then we start talking about, because we have to come back to talk about this responses later on. Wait a second, let me just watch a little bit here and okay. Let's go back a little bit. Sorry about this, because I think there's some repeat here. Alright, this is just a definition of transient response. Now we talk about the steady state response, and I'm going to talk about transient response a little bit because the response of dynamic system, we'll talk about transient response too. And here I just mentioned about this problem, same problem, we'll look at the transient response. What do we mean transient response? Is U1 equal to 0, so 0, 0, and this U1 is 0, so this is supposed to be 0. U1 is 0, this is 0, 0, and that's the formulation. I think the formulation is a little bit wrong here. So this is transient response. And the same thing, we talk about transient response means our input are 0, and that's we call transient response. I explained to you transient response already last week. And this is this week. And I'm using the same example, and I'm going to talk about transient response. I'm going to quickly just run this because we will come back to talk about that later. And because we don't have U1, then the transient response will give you the W1 is the relationship between W1 and W2. W1 is another one, W2. So this is our transient response formulations. I think I'm going to skip this one because we'll come back to talk about this later on. Okay, but the basic formulations for Kuhn mass Bamberg are derived in these chapters, and steady-state responses are computed for dimensionless equational motions. And I particularly point out this dimensionless. That means we talk about known units because it's more general to talk about dimensionless equational motions. The most important the items here is the frequency response functions. The frequency response functions are the one I explained already, are the one to illustrate the design of the QMB design. The QMB design. How good is your design? That's you can use the frequency response function to show that. Okay, I think this chapter is TMD. I will stop here, and I'm going to talk about now this chapter here. We call. Go back here. I got to turn this back. Okay, I'm going to talk about this. Okay, I'm going to talk about response of dynamic systems. Because how do you express your design? This is the way to do it. And I already showed you the frequency response functions. And here I'm going to show you more detail, explain to more physical meaning of the frequency response functions. That's what I'm going to do in the next 2 hours. Okay. let's look at this. The outline here, I will begin with the single degree freedoms, and I will talk about two degree freedoms. The two degree freedoms is similar to the TMB system. And I will talk about multiple degrees of freedoms, and then I will show the continuous equation of motions for being, and then I show more examples. Let's talk about the single degree freedoms first. Okay, this is the input part. I will talk more physical meaning of the system rather than just show you the mathematical formulations. Because if you just talk about mathematical formulations, then I don't think you will enjoy it too much. So, the way I will solve this equation of motion is in this way. Right? If I add an operator called d squared dt squared plus omega squared, if I do this and then I operate through these equations, you will find out that you will get this very neat equations. That means d squared over dt squared plus omega squared, and then d over dt plus a, and then parenthesis of w equal to 0. And this one, then you don't have to look at homogeneous solutions and particular solutions. You don't have to worry about those too. If you do this way, then you will solve homogeneous solution and particular solution in one equations, rather than you develop two parts. From here, you will get the we call characteristics equations. That means omega squared plus lambda squared plus omega squared, and then parenthesis lambda plus a equals 0. And this way is equivalent to you use exponential functions. I will show you exponential function later on. This is another way to solve differential equations. Okay, now, what do we mean the characteristics equations? The solution is this. So, if you look at carefully, these equations, then this equation include homogeneous solution and particular solutions in just only one form. That's the solution we get. Because lambda is plus or minus I, then we can write into C1 sine omega p plus C2 cosine omega p. Because lambda equal to mass A, then you can have C exponential minus AT. This is the way to solve differential equations. Alright? And then how we get, then if you sub this equation into original equations, that's what I do. You sub into original equation, you will find out that you will be able to find out C1 and C2. Because that C1 and C2, the matter of fact C1 and C2, those are your particular solution. And CE minus AT, that's your homogeneous equations. So, if I do this, then my solution will come out. So we can see this is the one way to solve a differential equation, a quick way to solve differential equation without going through the homogeneous part and particular part. That's one way to do it. Okay, well, this mathematically, there's just some tricks. It doesn't make any it's just easier to see it. But if you look at this, what does that mean physically? What will mean the sine omega t? What will mean cosine omega t? What will mean the exponential minus AT? What does that mean? That's more important than just this mathematical equations. Okay. Now look at what we mean about this. Okay. This is alright. We substitute here. And these are solutions. Look at this. This is our transient. And this is our steady state. So, that's what we want to see. So for any differential equations, even symplectical freedoms, we do have a transient part. We have steady state part. What do we mean transient? What do we mean steady state? That's why we want to talk about it. Take a break, 10 minutes.